Don't know if we are live. No. Okay. Hi, everybody. Welcome to a new session of Gimbalabs Playground. Today is July 24th, 2024. Our guest today is Claudio Hermida. He is a long-time Gimbalabs community member. And the topic he will present today is Cardano's EUTXO model revisit. This is our Gimbalabs Playground Miro. And here, Gimbalabs, this session takes place every Tuesday, 18 UTC. In this table, you can see all our past sessions. And you can see also our future sessions. Today, this is the Claudio session, Cardano EUTXO. And in our next sessions will be, because this is the season 3, and we have just a few next sessions. Our last session will be the 25th with Lucas presenting 45B, his company, and he will give us some updates from what's happening on the 45B planning. And if we have here the June 18, we have a slot, a free slot. So if you want to present, you can take it and bring us your proposal or idea or project that you have in mind. And to do so is really simple. You just have to go to this Miro board. I can share the link in the chat, and just you go and go here and select the only spot that we have free for this season 3. And that's it for my side. Thank you so much, Claudia, for being here and bring us this important topic in the Cardano architecture. Please go ahead.
Okay, thank you, Sebastian. Since this is recorded, I guess I'll introduce myself to everybody else who might watch it. I'm Claudio Hermida. I'm a computer scientist. My research interest is mostly the notational semantics and logics of programs, emphasis on categorical semantics, and my framework of reference is category theory. And over the last few years, I've been interested in crypto and blockchain. And serendipitously, last year, I found the excellent Gimbalabs Bluetooth PBL course. So that rekindled my interest in Cardano and made me want to try to understand it more thoughtfully. So this is the result of doing that. Basically, it struck me there are a number of concepts and techniques, if you want, from computer science, which are immediately relevant to when we want to understand Cardano's quite original, actually, EUTXO model of developing smart contracts. Okay, so let me share the screen to do the presentation. I cannot find where to share my. Okay. Can you see my?
Yes, we can.
Yeah, okay.
Yeah.
That's it? Okay. So let me go back to the beginning. Sorry, I was just reviewing my first set. Okay, so this is the thing. So what I want to tell you about these two major topics. First is how to handle state in functional programming and how that leads more or less immediately to having this notion of extended touch and transaction outputs that Cardano plays with. And the second thing, which is very original with Cardano, are the notion of validators. I want to show you how the notion of formal specification of methods, of contract methods, leads to having a notion of validator as well. And then we put all that together and tell you the answer to what is a smart contract in Cardano. Okay, so that's the plan for today. So in order to motivate this, I'm going to use a very simple toy example of a smart contract in Ethereum, the easier to understand, more intuitive, object-oriented counterpart of smart contracts as embodied by Ethereum. Okay, it's a very simple toy example, but it will help us to guide us along in introducing the various concepts involved. So let's look at this. It's a very simple vesting contract. It's nothing serious, really. It's just a silly toy example to play with the concepts at hand. So this is a simple vesting contract. The idea is that a benefactor can designate a beneficiary, deposits a certain amount of money in this contract, sets a deadline, and after that deadline has been reached, the beneficiary can claim the amount deposited. But before the deadline is reached, the benefactor can change his mind and cancel it and retract the amount he has deposited. So it's a very simple thing. It has data of this contract is beneficiary, benefactor, the amount to be transferred, the deadline, and it has a Boolean flag where the thing has been already been withdrawn or not to avoid multiple withdrawals, as we'll see later. This has to do with EUTXOs in an interesting way. And then it has simply the two methods, the claim and cancel. I'm not going to examine the code now because we're going to go over it in due time when we translate it to Cardano. Okay. So Cardano emphasizes the, so let me just give you a summary of what this is not the fully fledged formal definition of what the blockchain model is. That I have put notes of this talk where you can find all references to more detailed treatments of this. But this is enough for what I want to say in the talk. So the distributed ledger of the account-based model is simply a map around addresses to value and state. Okay, an account in Ethereum is identified uniquely by an address. Okay, and that account holds a balance. In the case of Ethereum, it's only Ether. But I'm anticipating we're going to use it for Cardano, which allows, besides the native asset ADA, it also allows non-native assets that you can mint. So value might be a more complex bag of things to play with. And the state will be like the local state variables, which simply support the business logic of the contract at hand, okay? Now, a smart contract in this setting is simply an object in the instance of object-oriented programming. A contract is a class, and the smart contract is an instance of that class, is an object. So it has a state that in particular includes balance and methods. So it has, as any object, has a bunch of data and methods that manipulate that data, okay? And now a transaction, what it does is simply takes the account ledger to the account ledger. It means that you effect a transaction, execute a method in the contract, and as a result, you update account balances, essentially. And you might also change local state, okay? But the essential thing that you update account balances. Okay, so now let's move to functional programming. Functional programming, the characteristics of interest in this context is that it's stateless, okay? In functional programming, the main objects of interest are functions. The function is evaluated, it takes inputs and evaluates it and produces outputs. But it does so without manipulating any state or storage variables. It's pure transformation from inputs to outputs, okay? As a consequence of that, and that's one of the values of it, probably the main value, is that it's referentially transparent, okay? An expression in functional programming, if it doesn't involve any input-output with the outside world, is pure. So it enables equational reasoning. You can replace any two equal expressions anywhere, okay? They always evaluate to the same value. Okay, so let's see how we can, if we want to reinterpret this stateful model of the blockchain proposed by the account-based model in a functional way. What do we do? Well, we had to reinterpret a state, okay? So the first thing, review how functional program can handle state. Let's see that. For imperative programming, a variable, okay, is essentially an object which has two methods, a read and an update, or if you want, a getter and a setter. Okay, now to emulate that storage variable in a stateless fashion, what do? We need to emulate these operations. So to emulate read, we need to provide the contents of the variable as an additional input. Remember, if the function needs any information, the only way you can get it is from its inputs. So if you're going to be able to read the content of a variable as an information to the function, you have to provide that explicit information as an additional input. And conversely, if you want to update that variable, well, you need to output that updated content as an additional output from the function, so that additional output can later be used as further input to another functions and proceed the computation, okay? So let's review this with a simple example to fix the concepts. There's a well-known algorithm to reverse a list using an accumulator, okay? Well, here we take list as an inductive structure where it's cheap to const elements at the beginning of the list, but it's expensive to add elements at the end of the list, okay? So if I want to do a naive recursive version of reverse, I would have to traverse the list several times if it becomes a quadratic algorithm by attaching elements at the end. So the effective solution to do that is one that you probably all know: use an accumulator variable, where you can compute the auxiliary result of the computation. So what do? We start with the empty list as accumulator, and then we add elements at the beginning of that list. So as we traverse the list and adding the elements to the accumulator, we obtain the reverse of the list. Okay, so essentially, when you reverse this auxiliary function, reverse with accumulator, when you do it to the empty list, you return the accumulator. That's your result. Okay. But if you apply it to a non-trivial list, an A and an L, what do? We update the accumulator by consting the first element at the beginning of the accumulator, and we recurse over the rest of the list. Then to actually compute the function we want, we initialize the accumulator with the empty list. Okay, we initialize the state, and we just call this function. Okay, now if we translate this, we're going to eliminate this variable accumulator to work in a purely functional manner. Okay, so what do? We transform the reverse with accumulator, but only had the list A argument to have the additional input state and additional output state, okay? So the first operation, when we process the empty list, what we have to do is read the state of the accumulator, but we just simply duplicate it, okay? We output the accumulator as result, and we keep the accumulator state unchanged. For the recursive version, what you do? Well, you're going to recurse the function on L and update the state by adding 8 at the beginning of the accumulator, okay? So that achieves the same result we had before. And then how do you call that function? Well, you call it with the initial state here, the empty list. And once you finish the computation, as it happens with the previous one, where accumulator is a local variable, at the end of the computation, it goes away, disappears. So we just project it out, we take the first component, okay? So that's the way that this is a very pervasive technique every time you use functional programming on how you deal with the state, okay? Like React components do that, for instance. So you find it anywhere you use functional programming. Okay, so now let's review what do we do, what's the state we need to program here. We say that the ledger is a mapping from addresses to value and state, okay? Now a map, you can model it as a list of entries to values, okay? So in this case, this map will be implemented as a list of triples, address, and associated value and state, with the caveat that the addresses are unique, okay? But essentially, as a state information, what we need to model is simply a triple: address, value, and state. And that's exactly what the EUTXO data comes to. Okay, so state remains associated to an address, and the address, the value, the state of the address associated to the account, we have conveniently split into value and storage. And we will see why later when we talk about balancing transactions. The values do have a special role in the transaction world. So we separate conveniently what is value or balance from the rest of the storage variables, okay? But basically, the data of a UTXO is that. It's an address, which is what we call the target address where the UTXO is held, the value, which is the value locked in this transaction output, and datum that can represent any kind of local state according to our needs in the contract logic. Okay, so that's the first part. However, this is just beyond the UTXOs as data. Cardano takes a step further and views UTXOs as resources. Let's come to that in a second. First, I'm going to tell you, so once we had this model of UTXOs as data, now the ledger in the blockchain and the UTXO blockchain model is very, very simple thing. It's just a collection of unspent transaction outputs. It's a set. That's it. Okay, there's no mapping, nothing. It's just a mere set of uniquely identified things. A transaction takes inputs to outputs. Okay, so the effect is a function on the ledger. Okay, it takes a ledger and produces a new ledger. And what's the effect? It takes a ledger, it consumes the inputs, and adds the outputs. Okay, so that's it really. That's the effect of a transaction in this model. As you see, it's a lot simpler in a way than the previous account-based one. But now let's look at that the EUTXOs are actually what we call resources in computer science. It's not just data, but it's data that can reproduce. Once it's produced, it can only be consumed once and only once. Okay, and this has to do with the actual value, as it were, monetary version of data in the blockchain. Okay, it can only be consumed once. That's very important, actually. It's a very important difference that Cardano does that the account-based model doesn't have. Furthermore, with the translation we had done, you can say one UTXO will be sufficient to account for the state of an address, of an account. However, Cardano allows to have that state split into several UTXOs, okay? You can have multiple UTXOs at a single address. That's why we can say that the state in Cardano is naturally sharded or split into these UTXOs. These two things are actually very, 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 very important consequences that make Cardano technically much more robust from a technical point of view, we'll see. Two things. First is the evident thing about efficiency, because in the transaction, we can select very precisely, if you want, with military precision, the pieces of state that we want to consume, okay? So different transactions that consume different pieces of state cannot interfere with each other. Therefore, they can be computed in parallel. Okay, so it's a natural parallel model there of computation for transactions, or in the case, validation. The second one, that has to do with our reasoning about the transactions and what they do. There's non-interference, as I said. A transaction, because it's a resource, a UTXO is a resource, it can only be consumed by a single transaction. So no two transactions can interfere over the same piece of state. Therefore, the transaction in Cardano is completely predictable, okay? If the inputs that we specify are available, they cannot be consumed by any other transaction, then they will be consumed by this transaction and its outputs is completely determined. This is a big difference with the account-based model, okay? Because in the account-based models, if I take a snapshot of the blockchain at the time I submit a contract call, by the time it actually gets executed, because I'm going to come to that difference in a second, by the time it gets executed, several other transactions have taken place and modify that global state. Therefore, in the account-based model, I can never, ever, ever be sure about what's the state in which the transaction is executed. I had to take all sort of precautions to make sure that I had to guarantee the conditions in which I'm assuming I'm executing. because there's no way I can know what the state is going to be. Okay. While in Cardano, because I can pinpoint exactly the EUTXOs I want to consume, I know exactly what's the state that the transaction is executed. Okay. So let's come now to the next major difference. This is already quite a difference, but let's come to the next major difference in Cardano transactions. I call this the most radical difference of the model. In the account-based models, all the transactions, those claim and cancel methods I showed you before in the Solidity contract, are executed on chain. All the nodes execute those transactions. Okay. In Cardano, we take a very different approach. A transaction is essentially computed off chain and only validated on chain. Okay, that bears repeating. You compute off chain and you validate on chain. Before going into the details, let's just say that that really makes sense. We know the basic premise that computing and storing data in a blockchain is expensive, especially relative to the off-chain world. Okay, so it really makes sense to limit, to do the bare minimum we need on chain for security, while we do as much as possible off chain for maximal computational efficiency. Okay, so Cardano takes that approach to its natural and logical conclusion by implementing this model. So this validation on chain is done by these things called validators. Okay, what's a validator? Validator is a Boolean valued function. It's a predicate. Okay, that takes three pieces of three arguments. The main one that you should focus on really is a redeemer. The redeemer is the action or method whose execution is being validated. Okay. Let's say in that case of the contract I mentioned, would be like the claim or the cancel methods would be the redeemers are being validated. Okay. Datum is the datum. This is a validator that's going to consume an input transaction. Okay, we're feeding an input transaction. We had to determine whether it's logically consistent with our program to consume this input. Okay, so this validator is going to tell you whether that's true or not. So in order to do that, it takes these pieces of data: the redeemer, which is a method that executing against this input. The datum comes from the input EUTXO. It's the datum of that piece of data. And the context, a strict context, it has two parts. One indicates a purpose of context. In Cardano, because you had non-native assets, before having a transaction to consume an input, you also have transactions to mint new values. And because of the consensus model, it has transactions to stake and take withdrawals from that staking rewards. So there are several kinds of transactions you can do. We're going to concentrate just in the ones that consume inputs, okay, which are the ones that are instrumental to implementing smart contract logic. The main thing about the context then is the transaction context. The transaction context tells you all the inputs, the output data that the transaction is going to produce, and the signatures involved. Okay, so to relate it back to our original way of thinking, the redeemer will be the actual input to the validator, while the datum is local state as an input, because we're modeling a state in a functional manner. And the script context is essentially the piece of global state that we also provide as an input. And this is a read-only state. You see, it produces a value result, but it doesn't update either datum nor script context. Okay. The validator is purely passive. It only reads the state and says yes or no. Okay. Now, input EUTXOs, there are two kinds. Essentially, there's a third one that's been added, but conceptually, there are two kinds. We have different execution logic. So the ones that have a public key hash address, those are unlocked by a private key signature. Okay. In the account-based model, the counterpart is what is called an externally owned account. Okay, so that would be a public key hash address. EUTXO held at one of those, and the script address, which is in the account-based world, will be an account address. Now, this script address has this property: you associated with the validator, okay? So you hash a validator code. We saw that what the validator was, this Boolean thing is coded in some Bluetooth or whatever. You hash it, and you obtain from that a valid script address that you can use as a target of TXOs. Now, any TXOs which is targeted at such a script address can only be unlocked, meaning consumed as an input, by evaluating the validator associated to that address and evaluating it successfully. Okay, so that's a role. Those are the two things we have. Let's move on. Now, let's go back to this idea I told you that in Cardano, transactions are computed off-chain, validated on-chain. So what do we do off-chain? We do the transaction building, okay? Transaction build, you specify the inputs, EUTXOs, and the would-be outputs, okay? We're gonna be the data, only the data part of the EUTXOs. I've been telling you EUTXO is just a triple of data, address, value, and datum. But in fact, that's just the data part. The resource nature of that is realized when we actually point to it uniquely by a reference. And the reference to EUTXO is given by the transaction that produces it, and its list, its index, which indicates its place in the output list, okay? A transaction takes a set of inputs, but a list of outputs, because we not identify within the outputs in which position the outputs occur. That way, a transaction ID and an index uniquely identifies an output of a transaction, okay? So when you can associate to that data, address, value, and datum, a unique reference to it, that becomes a resource, a EUTXO as a resource. So when we are building the transaction, we are specifying only the data, okay? So it's not a resource yet. It's gonna become a resource once the transaction gets validated. Then we are gonna have a transaction ID and an output index to refer to it, okay? So in the transaction build, we also indicate the signer, which pays the transaction fees and blah, blah, blah. These things, you know, that's not too important. Let me just show this. Now, in order to compute the data on those outputs, there's some computation that might take place. That would be the equivalent of what we call the method execution in the smart contract I showed you before, okay? So you need to compute like redistributing of balances and whatever output updates, datum updates you need to compute. Those are all computations that take place off-chain, okay? And that way we produce a transaction body. That's what we call a transaction body. Once we have that, then we pass to the next stage, which is you sign and submit the transaction for validation, okay? Now, how is it validated? Every input that is held at the public key hash is signature verified, while every input that is held at the script address triggers the execution of the corresponding validator, okay? Now, if all inputs in the transaction validate, then the thing is considered the transaction is successful. Now the ledgers get updated. The inputs are spent. I'll show you the effect of the thing. This one, okay? The inputs get consumed, so they're taken away from the collection of EUTXOs in the ledger, and the new outputs get added, okay? That's it. So that's the effect of the transaction. So you see how we separated this, we achieved this. So we basically do as much computation as possible off-chain, and then only use on-chain for the bare minimum necessary for security, which is validation, okay? So let me sum up some of the distinctions between the two models we've seen so far. In the account-based, what do you do? Well, transaction is signed and submitted to a node that will be common to both. But now the changes to the ledger are effected on-chain by means of stable dates, okay? There's a protected execution on-chain, okay? If anything fails in the transaction, it reverts to the initial state before the transaction execution. But notice that to achieve that, the machinery is more involved. You had to take a snapshot at the start of the execution of the blockchain. Because we execute everything on chain, there's this validation gets mixed with execution. When we see the code again, maybe I should see the code again to remind you. Here we have this, is in the body of the methods, we have required statements, okay? These required statements are validating the input state of the method, okay? And then we have this actual execution of computation, which makes a transfer from the contract account to the beneficiary. So the method embodies everything, validation and execution, okay? And you can intermingle them. I put here sequentially, it happens that all the validation is done before, but you can do some execution and then continue doing some validation, okay? So the things intermingle. While in Cardano, we do a very neat separation between computation and validation. Okay, that's an advantage. It's logically easier to think that way. Now, the other thing which is important is that in Ethereum, all the methods have unrestricted access to the whole global state. Okay. However, there are account-based models, other blockchains, which restrict the access to that, doing a similar thing to Cardano, where we limit the global state you can access to. Here we limit it with the transaction context. Say something like Algorand has a similar approach where you can specify which accounts you have access to during the execution of the method. So there's some similarities that you can implement. Or rather, there are some account-based models which are trying to incorporate these ideas from Cardano. Let's put it that way. Okay, now, while in the EUTXO model, what we have? Well, again, transaction assigned and submitted to a node. As I said, emphasize again, the outputs are pre-computed off-chain. Then the inputs outputs are fed to the Cardano node at transaction build time and subject to validation. Okay, so that's the main thing. So let's see a bit more about what validation really entails, okay? I'm telling you what the validator does, but we don't tell you how do you write the validator. Well, let's see what you write in the validator. There's something called specification in the small for methods via what we call pre and post conditions. Okay, so let me tell you what that is. Suppose you want to specify, let's start with a simple example to fix ideas. Suppose you have a sorting function that they simply know a list of integers and you want to return the list sorted in increasing order. So how do you specify that? Well, I cannot read the chat at the time, so if there's anything going on that I need to know, just just speak up, please. Anyway, so what do we need to specify the result of a sorting function? Well, the first thing we're going to say is that the output has to be increasingly ordered. Okay, so that's easy to specify. It's just simply any two consecutive entries in the list had to be less or equal than the next. Okay, so we require that for every list, the output of this function sort is ordered. Is that enough? Well, if you think of it, it's obviously not, because if that was true, I can just simply return over the empty list and I would satisfy the sorting requirement. Obviously, what we want is that the output list has a certain relationship to the original list we give as input. Namely, it has to be a permutation. So we specify there should be a permutation. So here you have a relation, a two-place predicate that takes, well, the first list is a permutation of the second. Okay, I specified this. It's rather easy to specify. And now we do have a complete specification. A sorting function is a function that returns both an ordered list that is a permutation of the original input. Okay, that's how you specify a list. Now we can apply that same idea to the methods of your contract. Okay, we look at the original method of the contract. We have the claim and cancel. And we can apply, we can say what's their specifications. I think before I'm going to give you another example here on Oh, yeah, I want to tell you a little bit more about the specifications in the formal setting. So in general, we are reasoning about functions, right? So we take a function from inputs to outputs. We want to specify what is called the extensional behavior, okay? For that, we're going to say that given an input that satisfies a certain precondition, the output should satisfy a post-condition, which is relates the inputs to the outputs, okay? So that's what's called a partial specification. It says that for every input that satisfies the precondition, the output has to satisfy the post-condition with respect to the input. Okay, so it's the kind of logical for an implication. If this holds, then this holds. Okay. Now, because we are in the blockchain world, we can say a bit more. Okay. What happens if the precondition doesn't hold? As we saw before, these requirement statements, or say if an input is not available in the transaction in Cardano, what happens? Well, nothing happens. In Cardano, just simply discard the transaction execution, and it will not take place. While in the account-based models, they had to revert. So it comes back to the original state. It has the same effect in the end. Okay. So basically, we want to say that the precondition doesn't hold. The thing should fail. Okay, so that's the thing. If not the precondition doesn't hold, then it should be false. Okay, so altogether, the specification for the function should be for every input. If the precondition holds, then the postcondition must relate the input and the output. And if the precondition doesn't hold, then it should be false. Okay. Now, if we massage that all together logically, it just comes to this simpler thing. So for all inputs, both the precondition and the postcondition should hold. That's it. Okay, so this is a formal specification of a method. As far as the extensional behavior is concerned, here we're not talking about complexity, resource consumption, or anything else. Okay, which is interesting from the logical point of view. What does this thing do? Okay. Now, I'm just giving you one more example that I think came from the Aiken library. The idea is to promote an arbitrary list of assets into a value. Okay. Now, this is taken literally. The text part is taken from the documentation. They do it in a twisted way. Say instead of telling you what's a precondition, it tells you what's the negation of the precondition. So, but anyway, I think you would understand. Say that this function fails if there's any duplicate amongst policy ID. This is because this list of lists is really implementing a map. Okay, so it's a map from policy ID to a map of asset name twins. And a map has to have unique entries on the first instance. Okay, and so this is saying there are no duplicates among policy IDs. This is the formal counterpart to that. Here there's a little ambiguity, says that there's no duplicates among asset names, but it's not duplicate among asset names only within the policy ID lists. Okay, it's not that there are no duplicates of asset names in the whole. So there's a little ambiguity. It's commonly found when you specify things simply in English or another other colloquial language, as opposed to using formal specifications, which are unambiguous. Okay, so here we're saying that all these lists should have non-repeated entries on the first asset name, but only within the policy ID. So that's a precise version of that. Well, it adds that the asset name has to be sorted within their list, but that's because that's just an efficiency consideration to speed up search when you're processing these lists. There's no logical consequence of that. And another convention here is that no quantity can be null. Okay, so none of the things could be null, could be zero. So that will be a precondition. And I think I studied the post conditions. Now the result should be the addition of values. By the way, the post condition is not specified. The result is not really part of the documentation. But so I'll tell you what it is. It's just every entry is a triple, policy ID, asset name, and an integer. You consider that to be a singleton value. Okay, have this function singleton value, turns that into values, and then you just put them all together. You just folder the monoid operation and empty. Okay. So that's just one example. Now, the question is now, what does it have to do with validators? Okay, so in the context of implementing a smart contract, a validator specifies the pre and post condition of a contract method. Okay, so when you see this validators function, which are just, as I told you, a function of 3 arguments that returns a Boolean, or even in the worst case, in that time version of Bluetooth, is a function with 3 arguments of time beaten data that returns nothing, you know? So it's not very enlightening to know what kind of use you're gonna do for this thing. Well, now we know a validator logically should encode the pre and post condition of the contract method. Okay, so of course, we're gonna show that with examples. So let's look at this, the function claim we were looking at before. It has 3 requirements. Okay, so the first requirement, you see that the 3 requirements are preconditions. This is precondition means, sorry. It means the transaction has to be signed by the beneficiary. This one, we check the current time, and we have to be past the deadline, so the deadline has already been reached. This one, because this has to do with the global nature of the state in the contract. I could be the beneficiary, okay? It can already be past the deadline. I do the withdrawal. There's nothing in this logic so far preventing me from doing that withdrawal again. The conditions will still be met, okay? So I had to indicate that the thing has been already withdrawn. I had consumed it. Now, this flag, what it really does is turn that little piece of state I'm consuming, namely the amount, into a resource. Okay, because the account-based model doesn't have this idea of resources that Cardano implements natively. I had to mimic that using this Boolean flag. Okay, if I do that, and then here I'm using a system method, transfer. It comes with its own pre and post conditions, okay? So in fact, as you can imagine, it's pretty easy in this case. A precondition this transfer method will have is that if I'm going to transfer an amount from this account, the balance has to be greater or equal to that amount. It has to be enough funds to transfer, okay? So that all these 4 form the precondition of the method. The post condition will be, obviously, I just simply make a transfer, okay? I'm not going to concentrate on consume because we are, as we see when going to relate it to Cardano, we forget about it. But the main part of the post condition we care about is the altering of balances of the account. Here I'm using the fact that we are having a before and after state, okay? So the balance of the contract before and the balance of the contract after, okay? So the balance of the contract after has to be equal to the one before minus the amount I had transferred. And conversely, the converse situation will be true for the beneficiary. The beneficiary will be equal to the beneficiary before plus the amount, okay? So that's our post condition. Okay, let's see how we're going to do that now in Cardano. Okay, so we're gonna start with we're gonna write the validator. You're gonna specify our best in datum and best in redeemer. So the best in datum has basically the same data we have seen in the Solidity contract, the 2 beneficiary and benefactor addresses, the deadline, and the amount. In this case, I'm not going to use the consume flags because the consume flag, as I just explained, is only there to mimic the resource nature of the EUTXO. In Cardano, the EUTXO is either present or already been consumed. So there's no need to have this Boolean flag to account for that, okay? So we're saving one byte of information. The redeemer, as I said, specify the methods. So it will be a list of alternatives with the signatures of the method. In this case, the name, and if we were to have any arguments, we'll put the arguments there as well. So in this case, we have the claim and cancel methods. And the validator takes datum, redeemer, and context and produces and tell me when it's true. And what we do a case analysis, okay? So in this case, I'm just going to write the one for the claim method, as you could imagine, the one for cancer is completely symmetrical, so there's no point in repeating it. So what do? We first write the preconditions, signed by beneficiary, we've seen before, and where the deadline has been reached. Okay. Remember in the previous one, we have also consume, but we don't need to worry about that. And now this extra precondition that says that there are enough funds to transfer, in our case, we are consuming specifically an input EUTXO that has that been held by the beneficiary. And because the transaction is balanced, if you're going to have an output of this amount, the balancing of the transaction guarantees that had to be an input of that amount as well, in total at least. So we don't need to check for this condition explicitly. The balancing of the transaction verifies that for us, okay? So we are reduced to checking these two preconditions, the signed by the beneficiary and deadline reach, okay? Now what we have to guarantee is a post-condition. The post-condition, what we have to address, we are consuming the EUTXO that handles the balance of the contract, essentially. The balance of the contract here, in our case, is represented by the value of the input EUTXO we are consuming. So we only have to take care about the value in the output EUTXO, the one we paid out to the beneficiary. So that's what we're going to do. Post-condition is to check that the amount paid to the beneficiary equals the amount specified in the contract, okay? And then you just put them all together. You do the conjunction, so that's our, okay? Is that more or less clear? You see how the specification gets reflected into validator code. So if you do that systematically, you have, I'm not saying it's easy to get the specifications, but that should tell you what, you should have an abstract notion of a method that you want to specify, and then you write the validator code using that. Okay. So I was just mentioning this. This is what I explained you about the flag, okay? We use that consume flag in the account-based model to reflect that that piece of state we had consumed, it was a resource. And so if we had already consumed it, we had to indicate that, because that's otherwise the contract doesn't know, because it just handles a global state. Okay. There's a converse, there's a counterpart to that, in the Solidity contract, we use a transfer method, which is primitive in the system. So it guarantees that the amount we say we transfer goes to the beneficiary. In the Cardano world, that's not the case in that sense that we are just simply consuming input EUTXOs, but there's no guarantee where that thing will go. Just imagine in this case, I can put a cute front end that fools a beneficiary to press a button claim. It will sign and say, oh, I claimed, I signed, nice. Where did the money go? Well, the malicious front end send that amount to any other address. As long as the account is balanced, there's nothing else that the validator will check, you see? So we had to explicitly specify that the amount is being paid to the beneficiary and has to be checked, okay? So as you see, there's always, when moving to the two models, there will be some pros and cons from each, but some things are automatic in one and some things are automatic in the other, okay? So just to wrap up this specification business, if you have a transaction, okay, with several inputs and several outputs, the transaction satisfies this specification. It has to satisfy all the validators of all the inputs. So you have a datum in one, a redeemer, and script context for 1 to n, and the preservation of values. This is the part that, well, I didn't write the formula. In the accompanying notes, you have more full-fledged details of this, if you want to say. But the preservation of values is, think of it as a physical law that, you know, like the preservation of energy. Energy is never created or destroyed, but only transformed. So the same is true with the values in blockchain, in a sense. So the sum of the values of the inputs plus the value minted, because here we are allowed to mint non-native assets, okay? So ADA is never created nor destroyed, it's always transferred, okay? But non-native assets can be minted and burned. So you had to take that into account in this situation. So basically, the preservation of value says that the sum of values of the inputs plus the value minted equal to the sum of values outputs plus the transaction fee. Okay. So this whole thing, you know, when you have, I'm going to say one more thing. Transactions in Cardano can be pretty complex because you allow several inputs that may be coming from different script addresses, okay? So you had to execute different logic for each one of them. And you had to make sure, because the transaction had to specify all of them, that this conjunction doesn't lead to any contradictions, okay, among the different methods and logics that you're using. So it could become a little trickier to I mean, not trigger, but it's a big piece of logical formulas to reason with at some point. Okay. Okay, so let me go to now introduce the notion of transaction schema. Okay. I was talking about building a transaction, but the transaction, as we say, takes very specific inputs. Okay. Now, the method we saw in the solidity contract claim works with any state you throw the transaction at, okay? You just call the transaction and whatever state it is in is executed, okay? So basically, to mimic the same possibility to call the contract at any point, you should be able to have a parameterized transaction body, that's what we call it a transaction schema, that takes any input EUTXOs you give them as formal arguments to build an actual transaction, concrete transaction with that data, with that EUTXOs data, okay? Now I'm gonna show you the example in code in a second. But that's just to put an idea, okay? Transaction schema is any function that outputs a transaction body using whatever parameters are appropriate to the logic of the contract we want to implement, okay? Think of it as analogous would be, if you're familiar with React, in React, a component is any function that outputs JSX, you know, the DSL language that React uses to represent the domain object model. So this is the same. It's a transaction schema would be a transaction body component, if you want to make the analogy. So what do? We take the claim method. So this would be a way to reason about this. We take the claim method becoming solidity with the requirement statements that become the precondition. And then they take the code which actually executes computations. Okay, so the requirements together with the post condition go to form the validator, while the code gets to be sent to a transaction schema. In this case, we call it EUTX claim. That's going to take as arguments an input EUTXO with all the details of the contract. In this case, the beneficiaries, the deadline, the amount, the transaction fee, and it's going to output a transaction in EUTXO with the amount to the beneficiary, plus a change address to pay to get whatever remains from the input transaction for the fees. And it's going to be sent to the beneficiary signature. So all this code is going to be like our transaction schema. Okay, so let's look at it in specific data. So I'm going to use for illustration, and because it's the only one I can seem to keep on using Haskell, Atlas. Atlas is developed by Genius Youth. And basically it's a revamped version of the Bluetooth application backend from IoG. Okay. There are two things that are interesting in this. You build transactions in a modular way via skeletons. They call them skeletons. You can add an input, you can add an output, a validity range, signature. All those pieces, you can be put them one by one, piece by piece, okay? So they are built into a TX skeleton monad. It has a monad structure to put pieces together, okay? And then once you have the skeleton, you have assembled all the data of the transaction, you pass it to a transaction builder, okay? that adds all the relevant parameters of interaction with the Cardano node. So it will be the network ID, data providers, whatever. So that will be our transaction schema, because we take all the data we need to build the transaction, we add all the network parameters, and we end up with transaction body that we can then submit for to sign and submit to the network. Okay. So let's the transaction builder, as you would expect, and you may be familiar if you play with the things at all, it will attempt to complete the transaction with using a coin selection algorithm to get the relevant fee. Also for the collateral input EUTXOs, which I'm not going to indulge in explaining what they are. It has to do with the current accounting model in Cardano. It might not be forever like that way. And it also attempt to balance the transaction, but sending any input value to a change address. Okay, this you do it in Cardano CLI, you do it in every framework you build transactions, you're gonna find these features. So let's look at a bit of code to get things more clearly. We already see on the validator for the claiming, for the claim. This is the transaction schema for that, okay? So what do? We are going to consume this claim is going to consume the input EUTXO that has the amount contributed by the benefactor. Okay, it's going to produce a skeleton that we're going to assemble into a transaction. So what do? You take the input EUTXO, you calculate the current slot, you extract the beneficiary from that reference. It is I assume I have it there as an inline datum. By the way, in the notes, you have more fledged version of this with all the helper functions. It's not going to bore you with all that. It's not really extremely relevant to what I'm presenting, though. So we calculate these two pieces of information, and here we start building the transaction. We set up a validity range because of the way the validator checks where the deadline has been reached. Your transaction cannot have an open-ended from infinity to infinity range. Transactions in Cardano have, you can specify a validity range. And in this case, we specify that the validity range is from this point onwards, okay? We check that, I wonder, we asked as a required signatory, the beneficiary, so we add this. So this will be added in the required signatories of the transaction. Then we have to specify that it might have an input, which is exactly the reference we are passing as an argument. You see, this is an argument to this transaction schema that gets used as a concrete input into the actual transaction. Okay, so this is the part. Here's where we connect our formal argument into an actual input for a concrete transaction. Okay, how do you do it? Well, you had to call all the things. We had to pass all the data, all the relevant data here for the input. The script is an ignorant datum, so I don't need to pass anything in that. And the redeemer, which is claim. Okay. And on top of that, that's the input I consume, and this is the output I produce. This is a transaction output. The out address is a beneficiary, and the value, which is the amount to transfer, I get it also from the input reference. Okay. There's no datum associated to this. It's a pure payment transaction, and there's no reference script. Okay, so that's that. And then we build a transaction doing this. You see, there's something called, but doesn't matter too much on the technicalities, as a monad node. So this is basically I'm going to submit something to a node, to a Cardano node. So besides sending the beneficiary, the claim vesting beneficiary, that's the type of that, just with the output ref, with the input reference, I had to provide the network ID, let's say testnet, mainnet, whatever, sanctionnet, the data providers, and the collateral. Okay, and once I had that transaction body built, there's a couple of typos there, remember to correct it in the notes. We submit, okay, and a signature. We sign with a private key and submit. Okay, so that's our transaction schema. Okay, so now we can tell you what the smart contract in Cardano is. Okay, It's a set of transactions. This is my putative answer. I think it's, I hope I convince you with all these arguments. I say maybe a reasonable one. So a Cardano smart contract is a set of transaction schemas and associated validators. Okay. Now, let's notice a few more things. Schemas and validators had to share, in some sense, the datum and redeemer. Remember that in Cardano, in the way it's set up, your validators and your on-chain code and your off-chain code could be written in different languages. Okay. Nevertheless, these languages will have to deal with the datum and redeemer as a common entity. Okay, although maybe written slightly different in one and the other, but there will be like a common entity that they have to share, which is the datum and redeemer, the state and the method names. Okay, so basically here the datum, remember, is a product of components of the local state of the contract besides the value. So it's of that type. It's usually a record type of this sort, as we've seen in the examples. While the redeemer is a sum type, okay, it's technically the product and sum types. That's it. Notice that these are the two primitive data constructors taken in special purpose languages like Aiken. Okay, the product types and sum types. These are enums, and these are just record types. Okay. Redeemer is a sum type whose alternatives are essentially the method signatures. Essentially. Method signatures. Okay, so redeemer will be method one with the types of these arguments to whatever number of methods we need. Okay. Now I had to say here the caveat: the correspondence of methods, as we saw in the Solidity contract, to the redeemer cases doesn't need to be 1-1. In this simple case, it would be 1-1. Okay, but the fact is, some methods may interact with various pieces of state that may require several inputs here. They will be consumed by different redeemers. Okay, so a method in Solidity contract may require to be translated into a transaction schema that involves executing different redeemers to validate different inputs in there. Okay. And as I say, conversely, because a transaction in Cardano can be quite complex, involving several inputs, and implements a business logic that you might need several conventional methods in the object-oriented sense to represent that. Okay, so the correspondence is not necessarily 1-1 for complicated things. Okay, it gets complicated, but in these simple cases, you basically see this 1-to-1 correspondence between methods in the Solidity contract and alternatives in the redeemer case. Okay. Okay, so I still have time to tell you a little bit more about deploying contracts. So far, we built a contract. As you know, as you might know, in the account-based model, once you declare this contract class, you deploy that contract. Deploying a contract means you create a new instance of that class, and you assign that instance to an account address. Okay, that account address is the one that's going to hold the local state of that contract. Okay. The initial state, you set it up in deployment by invoking the constructor method, if you recall, from the Solidity contract. So when you deploy the contract, you specify the parameters of that constructor method to set up the initial state of the contract. Okay. Now, one thing which is natural in the account-based model is that because it's a class, I can create several instances of that class. So I can create several instances of the same smart contract, as it were. Okay, each will be identified by a unique account address. What happens in Cardano? Well, the deployment of contracts in Cardano is basically amounts to this. First, you generate the script address of the validator corresponding to that contract. Remember, we have just one validator for the contract because it has several clauses for the different methods, right? So just like you have one piece of code for the smart contract in Solidity, you have one validator in Cardano. So you compute the script address from the validator. Okay. That is the cryptic address that's going to hold the local state of the contract via EUTXOs targeted at that address, okay? So here, so you construct the initial state. You build and submit a transaction with an output targeted, sorry for the typo, at that script address, okay? Which encodes the initial state of the instance in its value and data, okay? So it's analogous to executing the constructor method of the contract, where you deploy the contract, you get a unique address. The difference is that we don't have a unique address associated. We have an address associated to the class, okay, which is a validator, but we don't have a specific address associated to the contract itself. We'll see that in a second. So let me show you an example of this deployment. Place vesting, okay? It will take the data, all the arguments you need for setting up the initial state. So we need the benefactor, beneficiary, the deadline, and the value amount. And you build an output UTXO with inland data, in this case, where you specify all this data, okay? So the address is the vesting address. This is the address of the coded address of the validator, okay? The value, which is specified separately from the rest of the data, is the value amount, and then you build out the datum. Okay, so you take the this is dot from Plutus data, and you take the benefactor, beneficiary, you build a vesting datum record. Okay, with benefactor, beneficiary, deadline, and amount. Okay, then we specified further that we use an inland datum in this case, and there's no reference script. Okay, we're not using reference script. So this is the EUTXO, which sets up the initial state of the contract. Okay, and then we just complete the transaction with this skeleton and sign and submit. Okay, so that's the analogous of the deployment of a contract in Cardano. There's one more thing we can do there's something that happens in the smart contract world, in the account-based model, that we can also emulate, which is there's an operation called declaring a contract, which amounts to store the code on chain. So we can refer it to by other contracts as a library, and also we avoid storing the whole contract code in each instance that we create. Suppose we create several instances of the same contract, we will reproducing, wasting storage space, putting the code in each instance separately, because we had to have that information somehow. So if we declare the contract, we can just put the contract on chain in a certain address, and we can just point to that address whenever we need to execute methods of that contract. Okay. In Cardano, there's the same idea was implemented with this CIP33, which is a reference script. Okay. So we put the code of the validator in a EUTXO. In case you notice here, when I call here this witness, I had to pass in the whole validator script. So it's a whole piece of code I had to pass in this transaction build. Okay, which is a big chunk of data, as you may know. So this idea of the reference script, instead of passing the whole chunk of data, I can just put that data as a special field in a UTXO targeted to some address that I can then refer to directly instead of passing the code around. Okay. So the declaration can be done with a reference script. The other thing which is left to address is the fact that in the account-based models, I can create several instances of the same contract class, right? So here we have only one script address associated to that contract class. And I'm saying that the contract, I can emulate it by targeting EUTXOs at that address to represent the state. But what happens if I have several instances? How do I represent the several pieces of a state corresponding to the different instances without confusing them? Well, there's a technique you can use in Cardano, but you can take advantage of this minting of non-native assets. You can mint an NFT, okay, which identifies the specific instance of the contract address. You incorporate that NFT in the EUTXOs corresponding to that instance of the contract, And so you set it up in the initial state, and then you pass it along in the data and in the value of the EUTXOs belonging to that specific instance of the contract. Okay, so it's a lot of engineering that you had to do to mimic what happens in the account-based model in this case, but it's possible. Okay. Unfortunately, there's not a still established standard. If you see in the notes, I give you the quotes of what happens in the Cardano documentation. But it can be done. So this is an area that needs a lot more work. If there are no standards yet on how to handle this, but it's possible. Okay. And so basically, let me conclude with these things here. So a contract class basically is a validator script and transaction schemas. Okay. The object itself is deployed by an initial state EUTXO at the script address of the validator. A contract account address will be a contract token, the NFT that I just mentioned it, while the declaration will be, the analogs will be the reference script EUTXO. Okay. And that was it. Well, I have 10 more minutes, so let me confuse you completely with one more piece of trivia for you to handle. This is just for you. Some of you are not functional programmers, so anybody who has doubled in Haskell, they may have come across their use of monads. Okay, in particular, the state in Haskell, people might think, oh, this is handled by the state monad, and indeed it is. But so let me show you how it relates to the version I gave you. The state monad, there's this, recall you this correspondence between a function that take a pair as argument and a function that takes two inputs as arguments. Okay, so it's called carry and a carry. Okay, it's a carry is also in the name in homage to Haskell B. Carry, who is also an honor in the Haskell language, British logician who developed combinatory logic. Okay, so carry is just simply this operation. Okay, you take a function that takes a pair of arguments and produces a function that takes one argument at a time. So it takes an A, takes a B, and applies F to the pair A and B. And it has the converse operation. So this is what we call an isomorphism between these two types. Okay, so now apply this to our functions that carry a state. It's a function from IS to OS. If I carry it, I get this a function, sorry for the typo there, a function from I to the type S function OS, okay? This is exactly what is called the state monad. The state monad at type O is S arrow OS, okay? So a function with from I to O with the state S corresponds to what is called a monadic computation from I to the state monad at O, okay? So it's entirely equivalent. This naive, I think this is more intuitive to treat a state as an additional input and an additional output, but you can represent it this way and have the advantage of incorporating into the monad framework in Haskell and do monadic composition and blah, blah, blah. So I just wanted to let you know that they're equivalent things, so it's not different. Okay, so I managed to finish in time. So if any questions, maybe I should drop in the chat the reference to the repo where you can read the notes on this if you want to see this in more detail.
Yeah.
That's it. Okay, Sebastian, you tell me what's next.
Man, this was fantastic.
Well, it's recorded, so if there's anything you really want to go with it and listen to it again, you have it. At least I try to give you a guide to. The note is a little more full-fledged and so hopefully more explanatory. So there you have all the details you might need.
Yeah, but this for me it was a really good looking of the both models. Fantastic. I have to check again the recording. Thanks a lot.
Thank you.
For this
No, you're
explanation.
welcome. Thanks for listening. Thanks for your patience.
No, not at all. Fantastic presentation. If you have questions, please go ahead.
Hi, no questions, Claudio. Thank you. But just wanted to say thank you for that. That was a deep dive. A lot of it was way over my head, but I'll certainly catch up on the recording again, go over it again. It was great.
Thank you, Jonathan. I mean, I think the notes will give you more details than you know. I think I did a better job with the notes than my presentation for sure. So have a look at them and give me feedback. My idea was to turn those notes into some blog posts. So whatever feedback I get and what needs to be better explained, I would appreciate.
Yeah, no, I'll go through that as well. Thank you.
Yeah, okay. Thanks a lot.
Okay, guys.
Okay.
Thanks for listening. See you next time. See you around in the open spaces.
Sure. See you tomorrow.
Cheers.
See you guys. Thanks for coming.
Thank you.
Bye-bye.